Hey out there in King William County, this is Tracy Folks, and I'm ready to talk to you about Chapter 14, which is Kinetics. Now, we did not touch on Kinetics much last year because we were on that kind of hybrid schedule, so we didn't have time to talk about the rates of reactions very much. And we briefly talked about how if you heat up a reaction, the rate will increase and it will react faster. But we're really going to dive into some rate laws in Chapter 14. Now, Chapter 14 starts off talking about concentration of reactants. The greater the concentration, the greater the number of particles in your solution, the greater the number of collisions, and the more collisions you have, the better chance you have of bumping up into the right chemical and reacting. So your rate goes up. So if I increase the concentration, I expect the rate to go up because I have more particles having a higher chance of bumping into each other the right way to react. Temperature. And the middle school teachers do a really good job of this in teaching you that the hotter something is, the greater its kinetic energy. The greater its kinetic energy, the faster it moves. The faster it moves, the greater the chance it's going to hit something and react. Now, I know concentration increases speed of reaction. I know that temperature is going to increase the speed of reaction. But does every time those particles bump, do they react? Heck no. You got to bump in just the right way, okay? So structure and orientation are going to play a big part on whether or not that reaction goes through and what your rate looks like. So you have to bump up on that molecule just the right way. Back it up on that molecule just the right way for it to react so that the rate increases, okay? Now, the first example I did, and these examples and all of these notes are hooked up in Schoology for your viewing pleasure and review, okay? So the first example I did, I gave you this equation. Okay? And I gave you that equation, and I said in the first 10 seconds of the reaction, the concentration of this goes from 1 molar to 0.868 molar, and that all happens over 10 seconds, okay? And the first thing I did is I asked you to calculate the average rate of the reaction in this time interval. All right, so rate is going to equal negative 1/3. Why negative 1/3? This 3 comes from the number in the balanced equation. If this had been a 2, this would be negative 1/2. If this had been a 4, this would be negative 1/4. Okay, so that's where the first part of the equation comes from. And I want the change in the concentration of that iodide ion over the change. And that's a lowercase t, that's going to mean time. Remember, up until this point, uppercase T has meant temperature, lowercase t is time, okay? And so I'm going to do just like I did before when we would do gas laws and things, delta T or specific heat equations. It's final minus initial. So the final concentration is this. The initial concentration is that. So that's where those numbers come from, okay? Final time is 10 seconds minus the original, which is 0 seconds. Okay, so that's pretty easy. I plug and chug this in my calculator. You should all be able to put this in your calculator. I get that number, all right? The units after that, molarity over seconds. That was molarity, that was seconds. That's why those are your units. Now, the second part of this reaction said, determine the rate of change in the concentration of the hydrogen ions during this time. So now, and I'm going to change colors just to make it easier to kind of visualize. I want to know what happened to that over that 10-second period. So rate's going to equal negative. Because this is a 2 here, negative 1/2. Change in the hydrogen concentration over change in time. Again, T is lowercase t for time. I know the rate of this reaction. I just found it. So looking for this, so that's going to become my x over the change in time, 10 seconds, all right? And you should all be able to solve for x at this point in your super chemist career. Again, units are just molarity. Oopsie doopsie, because that's just that. All right, so that was our first example on doing an actual rate equation. Again, this is new to you. We did not get to this last year. All right. The next part of your notes starts talking about rate laws. Rate laws are equations we can use to determine concentration and rates of reactions. What I want you to pay particular attention to are the exponents right here. Okay. These exponents up here are not necessarily the same as the coefficients in the balanced equation. Now, there are 3 types of reaction orders that chapter 14 does talk about, okay? And we're going to talk about all 3. And those 3 orders are 0 order, 1st order, and 2nd order. 0 order, the rate is independent of concentration. It doesn't matter how concentrated that solution is, it's not going to affect how fast it goes. 1st order, rate is directly proportional to the concentration. And 2nd order, it's proportional to the square of the concentration. That's going to be really important to remember, okay? Now, one other thing I want to point out to you before we move away from this slide, okay? You can look at a rate law and easily determine if it's 0, 1st, or 2nd order, okay? If it's rate equals K and there's no concentration in it, it's 0 order. If it's rate equals K, I'm just going to put X here and it looks like that, whatever X is, this is 1st order because that exponent is a 1. And that's 2nd order because that exponent is a 2. 2nd order, 1st order, 0 order because it's not there. K is a constant value, and it's something you will either be given or something that you will be searching for in the problem. All right? Now, I know how much you loved Clausius Clapper on graphing and Google Sheets, okay? We're going back to Google Sheets again, and we're going to do some graphing with rate laws. Now, you guys should be pros at putting in information in spreadsheets now and creating charts and finding line equations, all that good stuff we did back in, I think it was chapter 11. And the reason we're going to be graphing is we can graph concentration versus time, and that is another way for us to determine if something is 0, 1st order, or 2nd order, okay? Now, I want to go over a quick and easy way to determine whether or not something is 0, 1st, or 2nd order just by doing a quick look at the information given, all right? So the next slide in your notes says determine the order of reaction, all right? Now, if you look at the information here, if you look at the concentration, it doubles. And every time the concentration doubles, the rate doubles. They are directly proportional then. As one doubles, the other doubles, all right? If you are directly proportional, you are 1st order, so your rate equals K times the concentration of A. Now, if you look at the next example, okay? Here we go. I'm looking at, wait a minute, this one right over here, this one. As the concentration doubles, guess what? There's no change in the rate. So concentration does not affect rate, so this is 0 order, so rate equals K. And then if you look over here, as concentration doubles, holy schmoly, the rate does more than double. It's like crazy poo, right? When it's not doubling and it's not changing, it's 2nd order. And that's the easiest way I can tell you to remember that. Concentration is doubling over here. The rate is doing more than doubling. It's 2nd order. Now, sometimes in your equation, you're going to have more than just one reactant. You're going to have multiple reactants. And that's where things can get a little crazy. You can say that there are 3 orders. You can say that maybe it's 1st order in respect to A because A has an exponent of 1, or 2nd order in respect to B. but the overall order of the reaction, you have to add those exponents, okay? Now, I want to go ahead and do another example, okay? And this example is in your notes, and you can hit pause if you need to just stare at this for a minute while I talk about it on the board, okay? Because I'm showing you my work as well. So it says the initial rate of the reaction is measured at several different concentrations, and that's what the information in the table is giving you. From the data, determine the rate law for this reaction and the value for K. Well, if you look at this information, okay, every time NO2 doubles, the rate goes up by 4. So NO2 must be second order. And then if you look at the middle column, if you double CO, the rate stays the same. So CO is having no effect, or carbon monoxide is having no effect on that rate. So that must not be a part of the rate law. So the rate law should look like that. No CO2 and no carbon monoxide in that, because when carbon monoxide doubled here, the rate stayed the same. And how do I know that? I looked at experiment 2 and 3. Carbon monoxide doubled, rate did nothing. Okay? Now, I'm going to use the information from number 1 in the data table. All right? I got a whole data table there. I know in number 1 that the rate is 0.0021. I'm looking for K, and I know the concentration in number 1 for NO2, or nitrogen dioxide, is that, and I'm going to square it. Now all I have to do is solve for K. Shazammy poo-poo, I'm done. Okay, and we will dive into this in class a little more and really dig into that table. Really super easy. You have climbed the mountain, we are skipping down the other side. Okay? Alrighty poo. Now, Google Sheets, like I said, is coming back. Okay? And Google Sheets is coming back in the form of examples like this, graphing first order reactions. So, one of the easier ways to do it is if I tell you something is a first order reaction, you should be able to look back in the notes. Remember, I held up a slide that had 3 graphs on it. If something is first order, and I said this was first order, and you graph the natural log of the concentration versus time, you should get a line that looks like that. All right? The negative slope, so whatever the slope is, add a negative in front of it, it's going to equal K, which is that constant in the rate law. Okay? Now, for this one, I put all of this information already into my Google Sheet. And I found out that slope was negative 2.92 times 10 to the negative 4. And I found out that the y-intercept was negative 2.3. Okay? So I can put all of that into this formula that your textbook talks about. All right? And I can find out that K is a negative. Now I want to point out something. K is actually a positive number because a negative and a negative make a positive. This negative is part of the equation, okay? Now it says that I have at 865 seconds, that's the time. Oopsie, there we go. Plus the log of the concentration. Okay? You should be able to put all of that into your calculator and find out that X is equal to that amount. Okay? You will plug all of this in and get a number. You will do inverse log, which is just second log on your calculator. You'll get a little e, and this will give you your final answer of 0.017. This concludes part 1 of chapter 14 notes. Thanks for popping by. Bye. See you in class.